My beautiful students. Now in this video we will be discussing a new method that is used to find the forces inside the members. This method is called the method of sections. You remember in section 6.2 we studied the method of joints. We were just going to any point or any joint. We started to analyze the forces per joint. So we considered each joint as a particle and we started working from there. So we analyzed the whole forces in the whole member using that method. But now, in this method, the method of sections, sometimes we need to find forces in few number of members. So the number of members that we need to find the forces in is relatively small as compared to the whole number of the whole number of members in this truss. So instead of calculating the whole forces using the method of joints, we can use this method of sections, making sections in our truss to find desired forces in some members, not the whole members. So the idea is basically to cut the time and make a fewer number of steps to find our forces. Now, it says that this method is based on the principle that if the truss is in equilibrium, then any segment of the truss is also in equilibrium. So, assuming that, for example, we have a truss, the whole truss is in equilibrium. This is a given. We know for a fact that trusses are always in equilibrium, especially in statics, right? So, if the whole truss is under equilibrium, then also each member and each segment in that truss is in equilibrium. So for example, now take this member, for example. Let's assume that it was experiencing or exhibiting tensile forces. Then if we take a section inside this member, now this member will be divided into two segments, this one and this one. Now for each segment to be in equilibrium, if the whole member was under tensile stresses or tensile forces, then each joint or each end of this member must be under tensile. So here, this is the original tensile force. Then inside the member itself, inside the member here where we took this section, must be also under tensile forces. This situation also applies for compression. If this member was under compression, then compressive forces must be acting within the member itself. Okay? Now, let's assume that we have this kind of truss, and we were asked to find the forces inside members BC, GC, and GF. Now, if we follow the first method that we learned, the method of joints, then to find the forces in these members BC, right, we have to start at, for example, joint D and move from there. Join D, join C, and then find the forces. Or start at E, find all these forces, move to F, and then to C, and so on and so forth. This would be exhausting and time-consuming. And probably, if you faced such a problem in the exam, you will just spend more than half your exam just trying to find a force in, for example, one member, or two or three members. Now, the basic concept that we need to understand and follow is that if you make a section, so this is a section AA because we wanted to find forces in BC, GC, and GF. So you have to choose an appropriate section that would pass through your cut. Your cut should pass through all these members. Another important point is the maximum numbers of members that our section must pass through must not exceed three members at most. So here, section AA is passing through BC, GC, and GF, and that's it. If it were to pass through more than three, for example, 4 members and so on, then we will not be able to solve our problem because we are using 3 equations of equilibrium. Summation of forces in the x equals 0, in the y direction is 0, and moment around or about some point is 0. So 3 equations you can solve only for 3 unknowns if you take a section like this, for example. So remember, you use 3 equations, and our golden equation actually, remember, our golden equation in the method of sections is the moment equation. Why? We will discuss that later. Anyways, so you take a section where you can actually have a maximum of 3 members. And then you start solving your problem. You can solve for the right part or the left part. Actually, it's almost the same. But we will see how to choose the appropriate section now. That's it. Remember, you make a section that passes through a maximum of 3 members. You use your equations of equilibrium. Summation of forces in the y equals 0, and the x is 0, and moment about some point is 0. But before that, we might need, you see, just like 1 million lines under the word might. We might need to find the support reactions. Not always, but sometimes. We'll see how. Now, I will be solving a problem in the book. This is the problem 627. So this is chapter problems, chapter problem 627. Now look, the question now is asking us to determine the forces developed in members FE, so this member FE, member EB, so this member EB, so FE, EB, and BC. It's like this Z letter. It's just showing us a Z letter, something like Z letter. So we need to find the forces in these 3 members. Now, usually they tell you to find the support reactions before you start, but I advise you to do the following. Now, what you need to do is first determine the section you need to take or to make. So if I were you, I would say, we need these 3 members, then I would make this section here. Call it AA, BB, whatever you like. Now, we just said that we can actually work with the right side of the truss or the left side of that section. Anyways, 2 sections now, the right section and the left section. Now, look guys, if I were to work with the right hand side of this truss, the right side of this truss, then I would need this reaction at the roller. If I were to work with the left side, then I need this reaction here at the pen. The pen support, would give us reactions in the y direction and in the x direction. So you actually don't need to find all the support reactions. I would work with this side. I would prefer to work with this side, the right side. So basically, I just need to find this support reaction, dy. Now, but to find this dy, we have to work with the whole truss, right? The equilibrium. To find the support reactions, we have to work with the whole truss, because this support reaction definitely depends on this one as well. So make your section, decide which support reactions you need to work with. For example, here, this support reaction, and then using the equation of equilibrium, we would find the support reaction dy considering the whole truss. Okay? Now, I know for a fact that at A we have AY. Really? Play. Just give me a moment. So, we have AY and we have AX. Do we need to find AX and AY? Probably not. Probably yeah. Let's see. Anyways. Now, actually, probably I need to find the AY and AX. Anyways, maybe only AY. Probably only AY. Now, to find dy, definitely we cannot use the y-axis or summation of forces in the y or x. We need to find moment. So I would go and say we find summation. Well, just make it counterclockwise is positive. Summation of moment about point D equals 0. No, probably not. I'm sorry. So I would take moment about A equals 0. That's what I was saying actually. Sorry, I made a mistake. So here now, it's simple. AX and AY would cause zero moment about point A, so we don't actually care about their values. We just care about the dy and the other forces that have perpendicular distance from A. So now, start with this one. 11 kilonewtons going clockwise, so this is negative. Minus 11 multiplied by the perpendicular distance, which is 2. Minus 22 multiplied by the perpendicular distance, which is 3.5, right? 3.5. Plus a dy is going counterclockwise, so it's positive. Multiplied by 2 plus 2 plus 1.5, this is 5.5. This should be 0. So now dy would definitely give me a positive value. dy here should be 18 kilonewtons going in the positive direction or counterclockwise. Now, you see guys, we don't actually need to find AX and AY now, because why? Because we are working with this right side of the truss. So now you found your support or support reaction at D. Now you go and draw the part of the truss that you didn't cut actually. Now, so here the right hand side, right? We were saying that we need to work with the right hand side. So I don't know if I'm using the proper word, but anyways. Now here we have D. Here we have E, and then C, right? The distance is here. This is just for distances. This is 2 meters, and this one is 2 meters as well. So this is 2 meters. Now, the height is 2 meters for sure. Now, since we made our cut here, so we start drawing the forces. Now, we have this force EF, and we always assume that the force is leaving the joint, which means that the joint is in tension, under tension, or the member is under tension. So if it's leaving the joint, then it's leaving the member. Whenever it's leaving the member, that means it's tensile. Anyways, we assume it's tensile. So this is E. So this one should be force E towards F, right? And then we have here this force EB. So this is force EB, and we have force here leaving C. This is force CB. Now, what we need to do now is draw the line of action of these forces. So it's easier to start from here. So from FCB, it just goes towards, right? It goes towards point B. This is point B, or joint B. This one also goes toward joint B. Similarly, this one would go toward point F. So this is F. And it's okay now to just connect these lines together for distances only. So all these joints now are known: B, F, E, C, D, and that's it. Now, we were asked to find FCB, FEB, and FEF, right? EF, EB, and BC. As I just mentioned, or a while ago, I said that your golden rule that you need to use is the moment equation. The moment equation. Look guys, if I take moment around point E, or about point E, you would see that the lines of actions of these forces are actually passing through E. That means they would cause no moment. So immediately we would get rid of two unknowns. These two unknowns, we'll get rid of them, and we will just end up with FCB. I was sorry, I forgot to draw this force here, the reactionary force, right? This is dy, which was 18 kilonewtons going in the positive y direction. That's it. So now take in this direction positive, summation of moment around point E equals 0. So 18 kilonewton about or around point E is going counterclockwise, so this is positive. So 18 multiplied by the perpendicular distance, which is 2, minus, now we are left with only FCB. FCB, we're going clockwise, so this is negative. FCB multiplied by 2 equals 0. So FCB now should be equal to 18 kilonewtons. Now, since the sign is positive, then the force is tension. That means that the direction that we assumed for the force leaving the joint is right. It was correct. So it's also leaving the member. That means our member is under tensile forces. Now we need to find the other two forces. Again, we need to use our golden rule. Why? Because if the line of action of one force passes through one point, then it would cause 0 moment. So if we take moment around B, we will get 0 moment around B caused by force FEB. So we will get rid of this one. This one is known, right? We just calculated that. And we are left with this one, FEF. Or you could find moment around or about point F. But the perpendicular distance is somehow probably confusing here between FEB and F. Somehow, not really difficult, but somehow confusing. So I would rather to work with the moment about point B. So again, this direction, moment is positive, summation of moment around B equals 0. So we will get F EF multiplied by the perpendicular distance, which is 2, minus. Now, I forgot to write down this force as well. I'm sorry. So this is 22 kilonewtons. Minus 22. So 22 about point B. This is going clockwise. Sorry. So that's why it's negative. Minus 22 multiplied by this distance. This distance is 1.5. So this is 1.5, right? We know it's 1.5. Multiplied by 1.5 plus 18 kilonewtons, which is the support reaction, multiplied by 3.5 perpendicular distance. This is 0. This would give us a value of FEF would be, FEF would have a value of minus 15 kilonewtons. Minus 15 kilonewtons means our force is of compressive nature. Why? Because the direction that we assumed is the wrong direction. So we have to make this force go into the joint, meaning it goes into the member. So FEF is or has compressive nature. So this is, we could write it as 15 kilonewtons compression. Okay? Now, the last thing that is left there is this one, FEB. Now, remember guys, we just used one equation. We have 3 equations, summation of forces in the x equals 0 and the y equals 0 and so on. Now, we could analyze this force on the y-axis or on the x-axis and then sum up the forces to get our FEB. Either is fine. Either is fine. You just need to find this angle. Now, this angle, you could either find the tan inverse and so on, but I always prefer to work with the slope. So if this was 2 meters, this height was 2 meters, this is 1.5, then immediately this from Pythagorean theorem, this length would be 2.5 meters. 2.5 meters. Okay, so the component of this force on the x-axis is 1.5 over 2.5 multiplied by FEB. So here you could say this one is really, really tiny, but I'll try to maximize it. Here would be 1.5, yeah, because we're looking for the x component. So 1.5 over 2.5 multiplied by FEB. So we just sum them up in the x direction, and that's it. So now minus 1.5 over 2.5 FEB, sorry, plus, now FEF, we said that the direction that we assumed was wrong, right? So we have to take the other direction. That means it's going into the joint from left to right. So now it should have a positive value, plus 15, right? Plus 15. Now we also have this force, which is FCB, right? FCB is going in this direction, in the negative x direction. So minus 18 equals 0. So now FEB would give me a negative value of minus 5 kilonewtons. Again, FEB is basically, or this direction is wrong. It should be going into the joint. That means FEB has a value of 5 kilonewtons, and it has compressive nature. That's it. So you see, guys, the important point is to determine what kind of support reactions that we actually need. You could actually calculate all of them at the beginning, but you don't need them. So if I were to work with this section, again, we make a section where we have a maximum of 3 unknowns, or they should pass through, or this section should pass through a maximum of 3 members that we need to work with. And then simply you just use the equations of equilibrium. The golden rule is the moment about some point. So to cancel out, for example, 2 unknowns, you are left with the third one, for example, and that's it. You find it, and then you take moment about another point, and so on and so forth. Use your summation of forces in the x and y and so on. So here, sorry, I should have written that here I used this rule, summation of forces in the x is 0. That's it. So this is problem 27. We will solve another problem later, hopefully tonight. Thank you very much, and see you.